Waveguides, fields and waves in rectangular waveguides. First part, series on microwave engineering, lecture number 1.20. Hollow pipe waveguides are transmission lines capable of carrying high frequency non-TEM waves or signals. Ordinary transmission lines like parallel wire lines, they cannot carry such a high frequency waves. When the cross section is rectangular, the hollow pipe waveguide is called rectangular waveguide. In the present session, our focus is on finding fields inside a rectangular waveguide when it is carrying a high frequency traveling wave. First, let us concentrate on the structural features of the waveguide, that is rectangular waveguide. These features we can see soon. They go into the analysis of the waveguide. Let us suppose rectangular waveguide has inner dimensions A and B. These are standard symbols A and B. A more than B. Also suppose guide is lying along z-axis. Guide is very long, so there is no possibility for the existence of a reflected wave or standing wave. Only pure traveling wave is present in the guide. Walls of the guide we assume are made with perfect conductor. Sigma conductivity very high, tending to infinity for the walls. Hollow region is assumed to be perfect dielectric. It implies sigma is 0. But in practice, infinity 0 or conductivity is not achievable. Assuming sinusoidal time variations, the task is what are the field components? What is E? What is H? What is EX, EY, EZ? What is HX, HY, HZ in the guide? Entire analysis is done in phasor domain. Here is shown a rectangular waveguide, two broader walls, two narrow walls, a flange is there to connect waveguide with another waveguide. Now, for the purpose of analysis, this guide has been placed along z-axis and broader walls are, one broader wall is over xz plane, another broader wall is at a distance of B from the bottom broader wall. Two side walls are narrow walls, one narrow wall is over yz plane, another narrow wall is at a distance of A from the first narrow. And as already mentioned, the guide is carrying a traveling wave at a point in the hollow region, at an arbitrary point somewhere here. What is E? What is H? This is the problem. This is the issue which we are going to address right now. Finding fields inside the guide is a multi-step process. Mainly two steps are there. In the first step, transverse components are expressed in terms of longitudinal ones. Transverse means transverse, normal to the direction of propagation. Longitudinal means parallel to the direction of propagation. Wave is assumed to be traveling in z direction. Therefore, EZ, HZ, they are longitudinal components. Other components, EX, EY, HX, HY, they become transverse components. In the second step, longitudinal components are found using wave equation. In the first step, transverse components are expressed in terms of longitudinal components. In the second step, longitudinal components are obtained using wave equation. Once longitudinal components are available, we can substitute them in the relations obtained in the first step to get all the field components. This is the overall picture. Let us do first step in this session, second step in the next session. Let us define the problem by specifying the structure and its constitutive parameters. This is the starting point. We consider waveguide. So waveguide means rectangular waveguide, four walls, two narrow walls. Walls are made with conductor. We assume the walls are made with perfect conductor. And these walls enclose certain region. It is called hollow region. We assume it as a perfect dielectric. So sigma is 0 for the hollow region. It is a dielectric. So mu is mu naught. Epsilon is epsilon. Select appropriate coordinate system. Place the structure in the system. Rectangular waveguide exhibits rectangular symmetry. So Cartesian system is the most appropriate one for the present case. Consider Maxwell's curl equations. Expand them to get two sets, a total of 6 component equations. So Maxwell's equations we consider curl equations. One is Faraday's law, another is Ampere-Maxwell's law. These two we consider, we expand them. we get 6 component equations. Selecting from one from each set, relations for transverse components in terms of longitudinal ones are derived. So first step, total picture pertaining to first step is given here. In general, E is a vector, H is also a vector. We are considering the problem in a Cartesian system. Therefore, E in its component form is Ex x cap, Ey y cap, Ez z cap with plus in between. H similarly H. As guide is traveling along z direction, wave is traveling in z direction. Ex, Ey, Hx, Hy are normal or transverse components, and Ez, Hz are longitudinal components. In general, each component, let us say Ex, it is function of x, y, z position as well as time. Note, wave is the property of dynamic field. Dynamic field means something which is varying with respect to time. So, field varies with respect to time. As this field belongs to wave. As wave is traveling in z direction and analysis is in phasor domain, we can consider Ex is, which is function of x, y, z, t in general. This is function of x, y, z, t. Wave is traveling in z direction. Therefore, z dependence can be expressed as e power minus gamma bar z. Time dependence. We are doing analysis in phasor domain. It means time variations are assumed to be sinusoidal. Therefore, time variations can be replaced by e power j omega t. Ultimately, we are left with Ex dependent upon xy. Actually, our now we require to find out dependence of E over x and y. So this kind of expression can be done for other components too. Now, Maxwell's curl equations. Del cross H equal to j omega epsilon E. This is Ampere's law. Ampere, Maxwell's law. Actual law is this one, del cross H equal to sigma E plus j omega epsilon E. But we want field at a point in the hollow region where conductivity is 0. Here I want fields. Conductivity is 0. Therefore, this fellow becomes 0. You are left behind this one. Next equation is Faraday's law. In these equations, these are actually vector equations. We can expand them to get curl H, curl E. We can expand or we can convert them, or we can find their component equations. Now, wave motion is in z direction, and hence dou by dou z is minus gamma bar. While expanding del cross H or curl H, while expanding curl E. Curl H means x cap, y cap, z cap, dou by dou x, dou by dou y, dou by dou z. Dou by dou z is there. And then third row is hx, hy, hz. As wave motion is in z direction, in place of dou by dou z in the expansion, we can simply put minus gamma bar. So this is del cross H, this is del cross E. Expanding del cross E, we got this determinant. Dou by dou z has been replaced by gamma bar. Hx, hy, hz. Similarly, dou by dou z here replaced. So del cross H equal to j omega E, j omega epsilon E, j omega epsilon E. E is Ex, Ey, Ez. Here it is minus j omega mu H, therefore minus Hx. Now this determinant can be expanded. We get x component, we get y component, we get z component. X component can be equated to j omega epsilon Ex, y component can be equated to Ey, z component to j omega epsilon Ez. So 3 equations. They are scalar equations. Similarly, here also we get another 3 equations, scalar equations. Total we have 6 equations. So we manipulate these 6 equations to express Ex, Ey, Hx, Hy in terms of Ez, Hz. Then the resultant relations are Hx. You see here, Hx equal to minus gamma bar by h square, dou Hz by dou x. Hz is z component of H, longitudinal component of magnetic field Ez. This is electric field component along the direction of propagation. So here also Hz, Ez, Hz, Hz. See, notice on the left hand side you have transverse components. On the right hand side, these equations involve longitudinal components. So this set of 4 equations, they give transverse components in terms of longitudinal components. These equations involve gamma. What is gamma? Gamma is propagation constant. Bar is used to indicate that the wave inside the waveguide is non-TEM wave. Simply gamma means it belongs to TEM. Bar means it is non-TEM. You are going to see TEM wave cannot exist inside the waveguide, hollow pipe waveguide. It is non-TEM. Gamma pertaining to non-TEM is usually indicated with a bar. H. What is H? Here is shown H. H square is gamma square plus omega square, frequency square. Mu and epsilon, these are constitutive parameters of the hollow region. How we got these equations? These are by manipulating the 6 equations which we had in the last slide. One can notice from those expressions, with both longitudinal components 0, that is Ez0, Hz0 simultaneously, all the field components become 0, indicating a wave with the components transverse electromagnetic wave or TEM wave it is called. It cannot exist inside a waveguide. For example, put Hz0, Ez0, Hz0, Ez0, Ez0, Hz0, Ez0, Hz0. What is happening here? Hx, Hy, Ex, Ey all are becoming zeros. So, in total, Ex, Ey, Ez, Hx, Hy, Az, all 0. It means E is 0, H is 0. It means both the fields are 0, therefore wave is 0. Wave cannot exist. Therefore, with Ez, Hz, 0, wave cannot exist. Ez0, Hz0 means it is a TEM wave. TEM wave cannot exist. With Ez0, Hz not equal to 0, Hz 0. Ez not equal to 0, Hz 0. This wave is called TM. TM means transverse magnetic. Here magnetic vector is, see this is direction of propagation. Hz 0 means H is perpendicular to direction of propagation entirely. Ez not 0 means E is like this. It is having a component along direction of propagation. So TEM wave. This is TM wave with the Ez not 0, Hz 0 is TM wave. All the components are not 0. So there is a possibility for the existence of wave in the waveguide. This wave is called, as already mentioned, TM wave. When Ez 0, Hz not equal to 0, in this case also there is a possibility for the existence of a wave because certain components Ex, Ey, Hx, Hy, out of these 4, certain components are non-zero. Of course, Hz is not 0. So Hz is not 0. Some transverse components are also not 0. Therefore, it means field is there, wave exists. It implies wave exists. This wave is called transverse electric. Why it is transverse electric? This is direction of propagation, Z. Transverse electric means electric vector is entirely normal to direction of propagation. This is E. Ez0. No component along Z direction. Hz not 0 means H may be like this. It is having a component along Z direction, a normal component also it may have. With the Ez not 0, Hz not 0. Ex, Ey, Hx, Hy, they are all non-zeros. So wave exists. This wave is called hybrid or mixed wave. There's a name for this. It is called hybrid or mixed wave or TE plus TM wave, as it is combination of TM and TE wave. So this is what I would like to share with you in the present session. In the next session, we focus on solving wave equation to find out longitudinal components, that is Ez and Hz. Once Ez, Hz are available, they can be substituted in the expressions which we have derived here for Hx, Hy, Ex, Ey to find the field that are part of wave motion inside the waveguide. Enough.